This is part 2 of our 7172 notes on the mean and standard deviation of the sample mean. So we're going to look at example 2, which is the standard deviation of the sample mean. And back to the example of the heights of starting players, we're going to determine the population standard deviation sigma. So recall that we often or recently have been calculating the sample standard deviation. So this is a slightly different equation that we would enter into Microsoft Excel, which is equals stdev.p. And then we would enter the 5 values for the 5 heights of our basketball players. And then likely we would have A1 colon A5. And when we pull that up, it's 3.4058, dot, 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 so 3.41. I highly recommend using Microsoft Excel for that. B asks us to obtain the standard deviation, sigma sub x bar, of the variable x bar for a sample of size, or for samples of size 2. So sigma sub x bar is going to equal, we're going to use our formula, which actually is on the next page, or we just take this population standard deviation and divide by the square root of n. So that's going to be 3.41 divided by the square root of 2. We can calculate that. So 3.41 divided by the square root of 2, we get 2.41. And that's for n equals 2. C is asking us to repeat part B for samples of size 1, 3, 4, and 5. So sigma sub x bar when we have a sample of size 3. So let's go back to 1 first, divided by the square root of 1. Well, that's just 1, so 3.41, that's when n equals 1. For sample of size 3, I can just go back up and change my 2 to a 3. It's 1.97, rounding to the nearest hundredth. That's when n equals 3. And then 3.41 divided by radical 4. Gives us 1.71. And finally, for n equals 5, we have 3.41 divided by radical 5. Or 1.52. And we'll enter those into our table here. So for sample of size 1, we had 3.41. Sample of size 2, we had 2.41. Sample of size 3, we have 1.97. Sample of size 4, we have 1.71. Sample of size 5, we have 1.52. And as you would expect, since we're dividing by larger and larger numbers, the standard deviation of the sample mean decreases, or the standard error decreases. Example 3, we have the mean and standard deviation of the sample mean. In this question, this is where you would refer to 7.2 in your text. So we're talking about living space of homes. As reported by the U.S. Census Bureau and current housing reports, the mean living space for single-family detached homes is 1,742 square feet. So I'm going to underline that. That's the mean. And this is talking about a U.S. census. So that means I know right now that my population mean is 1,742. And assume a standard deviation of 568 square feet. So again, with this being a census, this would be our sigma for our standard deviation of the population. A says, for samples of 25 single-family detached homes, determine the mean and standard deviation of the variable x bar. So for A, I know n equals 25. Mu, so the mean, we already know is 1,742. Since our mu and our mu sub x bar are equal. So that's when we have all possible samples of size 25. That's going to equal our population mean. And then for our standard deviation, that's when we're going to take our 568 square feet and divide it by the square root of 25. And we get 113.6. In part B, similarly, we're calculating the mean, and again, that'll be 1,742. And my sigma, sorry, that's sigma sub x bar. Sigma sub x bar equals 568 again, sigma, divided by the square root of now 500. So we've got 568 divided by the square root of 500, and we get 25.40. And again, we see that trend where with a larger sample size, we have a smaller standard error.